for coming out today to hear what Adam's got to tell us. Adam's a recent hire at University of Alaska Fairbanks as a postdoc in the Climate Adaptation Science Center's national program that puts together a cohort of fire scholars to look at impacts of climate change on fire and fire management around the country. So there's different regional aspects to that work. They work together as a cohort, as well as pursue their own projects in the regions where they're hired. And we're fortunate enough to have Adam working with us. His background is in boreal fire already. So he did work at University of Idaho on boreal fire in the past. And so we were really fortunate to have him come to work with us. He's going to talk today about some of the work that bridges that past stuff that he's done and where he's at now. And he's that program just got spun up, and it's only in the past couple months, I think since November, that he's been working directly with us. So we'll be fortunate enough to have him working with us for a little while. And with that, I'm just going to turn it over to you, Adam, so you can jump into your talk.
Great, yeah, thank you for having me today. I'm excited to share with you some of the work I've done. Yeah, as you said, a lot of the work I'm going to share with you was done as part of my dissertation at the University of Idaho. Since then, I did work for 3 years on a different postdoc at Northern Arizona University. But just recently, I've gone back into looking at fire-climate relationships and vegetation feedbacks in boreal forest ecosystems. So I'm going to share with you, the bulk of what I'll share with you was done in the past, but I do have some new results at the very end I'm going to kind of tell you about and kind of hint at where I'm going in the future. So with that, I'll just share my screen.
That looks good.
Great. Thank you. All right. So yeah, I'll just get right into this. So yeah, I'm Adam. I'm a postdoc at the University of Alaska Fairbanks, and I'm working in the Alaska Climate Adaptation Science Center. The project I'm working on, or my regional project in Alaska, is focused on trying to better understand and explore the interactions among climate, fire, and vegetation in boreal forest and tundra ecosystems in North America. And again, most of the work I'm going to share with you today was done previously during my dissertation, but there are some new results at the end I'll also kind of show you, and I also want to show you where this work is going to go in the future. Before I begin, though, I of course want to acknowledge and thank all the funding sources that have supported this work, both at my time at Idaho and currently at my current position. And also I want to thank all my committee members and my PhD advisor for all their advice and help on this work, as well as my current mentors on this project. So as many in the room are likely aware, there is a growing body of evidence that fire regimes have been shifting in recent decades. And not only do we see these changes in the past, we expect they're going to continue well into the future. When we look at boreal forest and Arctic tundra ecosystems specifically, we see that there are these really strong linkages between fire and climate during the historical period. When we model these past relationships and project them into the future using global climate model output, we see that there could be anywhere from a 50 to 300% increase in annual area burned by the end of the 21st century. Findings such as this, as well as this evidence for changing fire regimes, have really motivated and shaped my work. And the projects I've worked on in boreal forest ecosystems have tried to address three broad research questions. First, what are the most important controls of fire history or fire in these ecosystems during the historical period? So this wants to better understand what factors or what specific factors like vegetation and climate do we need to consider and put in our models that we want to predict how fire occurs across space and time. And not only do we want to understand what are the most important factors to consider, but what are the nature of these controls? How sensitive are fire regimes to a given change in climate or vegetation? And then how does the sensitivity change across different spatial and temporal scales? And then finally, can we use this information regarding what is controlled past fire activity in boreal forest and tundra ecosystems to say something about the future? How will fire regimes respond to future climate change? The first part of my talk is going to share a chapter of my PhD. And this chapter specifically looked at fire regimes and addressing these three questions in mainland Alaska. Here we're looking at a map of Alaska with 5 dominant vegetation types highlighted. And overlaying this vegetation map, we see fire history from 1950 to 2009. we see right off the bat, there's a lot of spatial heterogeneity regarding where we see fire versus where we don't see fire. For example, you probably picked off right off the bat that there's a lot more fire in boreal forest ecosystems relative to tundra, but this alone does not explain all of this variation. For example, we have regions in boreal forest that are very flammable. The most flammable ecoregion is the Yukon Flats located right here. And then we have other ecoregions in boreal forests that are much less flammable and have experienced very little fire activity of the historical period, like the Copper River Basin down here. We see the same pattern in tundra as well, where we have regions like the Southwest and the North Slope, which have had very little fire activity during that 60-year period, compared to regions like the Seward Peninsula and the Noatak River watershed, which have had much more. So what this project looked at was trying to better understand what is driving this long-term variation or spatial variability in fire across Alaska. And to do this, we used the presence absence approach. So specifically, we classified each pixel in Alaska at a 2-kilometer resolution as either 0 or 1, fire absence or presence. Using this presence or absence approach, we could then model explicitly the probability of fire occurring at a given pixel at multi-decadal timescales. To do this modeling, we use what are called boosted regression trees. And in these boosted regression tree models, we included 4 different explanatory variables. We included mean temperature of the warmest month, mean annual total moisture availability, which is just precipitation minus potential evapotranspiration. We also included a topographic ruggedness index and vegetation type, which was included as a categorical variable. Really, just to clarify and drive home what exactly we're doing in this analysis is we're not looking at interannual variations in the area burned. We're not looking at how interannual variability in climate influences fire. We're looking at how these long-term averages in climate over multiple decades, as well as these other landscape factors, influence that spatial variation in fire presence absence. We went ahead and we ran these models. And the first thing we're able to identify is what are the most important factors to consider or include in these models for predicting fire activity. And the 2 variables that consistently emerged as the most important were mean temperature of the warmest month and annual moisture availability, our 2 climate variables. So what we can do is we can go ahead and look at the relationships between this probability of fire occurrence and each of these climate variables more closely. And this is output from these boosted regression tree models that give us what are called partial relationship plots. So looking at these relationships between fire and mean temperature of the warmest month and mean annual total P minus PET, we notice some key features and patterns. First, we notice right off the bat that in the warmest and driest regions, this is where we're going to have the highest probability of fire occurring. This is not necessarily that surprising. It's what we would expect to occur from such results. However, there are other features and patterns that are more interesting. In particular, we see that these relationships between fire and climate are highly nonlinear. And in particular, let's take a closer look at this relationship between temperature and the probability of fire occurrence. We see what we're calling a climatic threshold to burning, and we were able to identify this threshold to be right around 13.4 degrees Celsius. Why we found these nonlinear relationships, and in particular this threshold, to be interesting is that in the context of understanding what's going to happen in the future, we can envision a scenario where we have a lot of land area in Alaska currently residing right below or near that threshold. And as climate continues to warm, which we know it will, more and more area is going to surpass that threshold and enter this region where there's a much higher probability of fire occurring climatologically. So the key points here are that we have these nonlinear fire-climate relationships with thresholds, and that small climatic changes can result in very dramatic increases in area burned or in the fire regime. We can look at how this will play out geographically using GCM output. So what we did is for a range of GCMs, we're just showing one as an example here, but for multiple GCMs, we downscaled their temperature data to the 2-kilometer resolution of our study. We then classified mean temperature of the warmest month relative to that 13.4 degree threshold. And we put it into 1 of 3 categories. It's either below that threshold, near that threshold, or well above that threshold. When we look at the historical period from 1971 to 2000, we see that most of that land area currently lies near that threshold. And as we go into the future, as conditions continue to warm, we see more and more areas no longer going to lie near that threshold, but well above it, in that region where there's a very high probability of fire occurring. To take this one step further, we can apply these climate data with our boosted regression tree models to make explicit projections of the probability of fire occurring in the future. What we did specifically is we transformed these probability values into fire rotation periods. If you're unfamiliar with what a fire rotation period is, it is the amount of time it takes to burn an area equal in size to a given area of interest. And as an example, we can look all the way on the left at during the historical period, where we see fire rotation periods for each ecoregion in Alaska calculated using historical data sets. Right off the bat, we can see that Yukon Flats ecoregion, where it has a fire rotation period of less than 100 years, and it's the most flammable ecoregion in Alaska. By comparison, we can also look at the North Slope, where it has a fire rotation period greater than 1,600 years. Using our projections in the future, we see that when going towards the end of the 21st century, there's going to be substantially more fire across the board in Alaska. In the interior region where the boreal forest is, we see that fire rotation periods are estimated to now be comparable to what is the most flammable ecoregion. Even more dramatically, we can look at those tundra regions. In the North Slope, we see that fire rotation periods in the future are projected to have fire rotation periods less than 200 years, which is a giant shift from where we would estimate them during the historical period. Now, considering these results, the first thing is that they are very dramatic. They're very striking. So we need to put them into a bit more context. The proper context to think about these projections is that these are climate-only projections of fire. They are not accounting for other factors that are also going to influence how fire regimes evolve in the future in Alaska. Most importantly, these are not accounting for changes in vegetation, which is going to take me to the next part of my talk. So when we consider changes in vegetation, we think that fire-induced changes in vegetation or fire vegetation feedbacks are also going to play a very large role, potentially mediating the direct effect of climate on fire activity in these ecosystems. What we can do to maybe first explore this is see how does vegetation change in response to fire and what are the effects. To do this, I ran analysis for just the boreal forest biome, but across all of North America. And we looked at tree cover data set from MODIS, which just gives you percent tree cover value per pixel. And what I did is I compared that percent value in the year prior to fire to the year after fire to get a relative change in tree cover. And we see, as we would expect, when there's more area burned, there's a much larger change in tree cover. And not only do we see that there's this large change in tree cover, we see that these changes can last for a very long time, decades. This is a figure on the right from Rogers et al. 2013. And in a similar analysis, they highlighted that these changes can last for decades. So not only can there be a large change in tree cover, but it can be persistent. So for the rest of my talk, we're going to explore more about what these fire vegetation feedbacks mean, and specifically, what is the evidence that they exist across the boreal forest biome in North America. When we consider fire vegetation feedbacks in boreal forest ecosystems, we think there are probably one of two pathways that can occur. First, there's a situation where there is very little or no fire vegetation feedback. This would occur where the vegetation that occurs during early succession is comparable in flammability to the vegetation community that preceded the fire event. By comparison, we could also have a negative fire vegetation feedback, and there is substantial evidence that these do occur in these ecosystems. This could occur if there's a decrease in stem density after fire during early succession, and this can last for a while, or there can be a shift to deciduous dominance. This would be a shift, and a shift to deciduous dominance would increase field moisture, therefore lowering flammability. So what we're going to do is we're going to test which one of these pathways is more prominent in the boreal forest biome of North America. And again, we're now extending it beyond Alaska to that entire region. So we're going all the way over to Eastern Canada as well. We're going to consider all these different ecoregions across this really broad study area. Our sampling unit has also changed for this analysis. We're no longer looking at the pixel scale. We're now summarizing our area burn data in what are called hexels. So what we did is we broke up our entire study area into 100 kilometer squared hexagons, and these are going to be our sampling units. For each year, we summarize total area burned within each one of these hexagons. And just to clarify, relative to what we were looking at in Alaska during the previous part of my talk, we're no longer looking at long-term averages. We're now looking at interannual kind of variations and summaries of area burned. So what we're going to do is we're going to test a null hypothesis that there is no fire vegetation feedback. And to do this, we're going to split up these hexels into two different populations. The single burn population is the collection of hexels where we get area burn values if it's the first or only time that hexel burned during our 36-year study period. Then we have a multi-burn population. These are area burn values per hexel if that hexel is burning for the second or more times during that same time period. We then ran a Monte Carlo sampling analysis. And essentially what this did is it tested this hypothesis. A bit more detail about how we went about this is we counted the total number of hexels that experienced any level of fire across our whole study area across all years. We then sampled that number, but only from the single burn distribution. We then calculate the total area burned across our entire study area and study period to get a single value. And we did this 1,000 times. If these two populations are the same, then the estimated total area burned should equal what we actually observed during that same time period using fire history data sets. However, if the multi-burn population is different and there's a negative fire vegetation feedback, this estimate should be higher than what we observed because this isn't accounting or including that feedback effect. And that's exactly what we found. We found significant evidence for a negative fire vegetation feedback across the boreal forest biome in North America using this approach. So the red X here, this is our observed total area burned across the entire study region across all 36 years. And then that black dot with the confidence interval, that's what we would expect under a null hypothesis of no feedback during that same time period. And what we see that is significantly greater than what we actually observed. We can do a bit of math to better understand the actual magnitude of this effect, and it's equal to 23,000 kilometers squared. So this is the amount of area burned that essentially did not occur because there was this negative feedback in place. Now, this is just our estimate, and also it's a bit hard to put this into context because we're looking at such a large study area over a pretty long time period. So to put in a bit more context, we can put this in terms of percent of actual observed area burned, and it equals about 3%. When we look at this way, this doesn't really seem like that much. But again, this is a really large study area. So the next part I'm going to show you is we broke up this analysis by ecoregion in Alaska. And we did a very similar analysis to what I just showed you, but instead of area burned, we're using fire rotation periods. And this was done to account for different sizes of these different ecoregions. So we went ahead and we ran this analysis for each ecoregion, and we can look at these results going from west to east across the study area. First thing to notice is that in most ecoregions, there is evidence of this negative fire vegetation feedback. There was only one ecoregion where we didn't really find any evidence. So while we did find evidence for negative feedback in most ecoregions, there is a lot of variability in actual feedback strength across the study area. And so kind of the final part of this talk that I'm going to go into is going to try to better understand what is driving this spatial variation in feedback strength across the boreal forest biome in North America. And we're going to look at this because this could potentially help explain or better understand how feedbacks in the future may mediate that direct effect of climate on fire activity in these ecosystems. When we want to consider what could be potentially driving the spatial variation in feedback strength, we consider two potential variables or explanations. The first was climate, and the second was vegetation composition. For climate, we're considering long-term climate in each ecoregion, and now we're looking at the fire weather index, not temperature or precipitation. The fire weather index is an indice from the Canadian Forest Fire and Danger Rating System, and this system effectively integrates temperature data, precipitation data, wind speed, and relative humidity. We averaged this value over the entire time period of our study area for each ecoregion. And just to kind of clarify, cooler and wetter values in the FWI are going to be lower, and then higher values of FWI are going to be hotter and drier regions. And ultimately, this will hopefully help us explain, for example, if regions are characteristically hotter and drier, do we see a stronger or weaker feedback strength in that ecosystem or in that ecoregion? We also looked at vegetation composition by ecoregion as well. And specifically, we just looked at the percent of each ecoregion that's dominated by either needle leaf or deciduous forests. So we can go ahead and look at the results from this analysis, and we see that there is a really strong relationship between average climate in each ecoregion and feedback strength, where ecoregions that are characteristically warmer and drier have a much stronger feedback effect associated with it. Now, this is a pretty clear result, but let's also look at the role of vegetation as well. And we see when we get to that is that there really is not much of a feedback, or I'm sorry, there is not much explanatory variable at all that we can get from forest composition in each ecoregion. So this relationship between feedback strength and climate is really interesting because, again, we're considering what's going to happen in the future as conditions continue to warm and become more conducive to fire activity in these ecosystems. As I highlighted previously, as these temperature thresholds are going to pass, we could expect large increases in fire activity if we're only considering how climate will drive fire. But we can also look at these projections of the fire index into the future. And we see that by the end of the 21st century, at least under the GCM we're looking at here, we're going to see these giant increases in fire weather index, the fire weather index as well. And so this suggests that that feedback strength could change and increase in the future, potentially mediating that direct effect of climate on fire activity in these ecosystems. And that's what we're working on now. Since I've started this new postdoc, this has been kind of the focus of my work. We've been trying to develop these models to model annual area burned in each ecoregion as a function of buildup index and the initial spread index. These are both indices from that Canadian Forest Fire and Danger Rating System I just showed with you. And the bottom line here is that when we look at these ecoregions and how well these models do at predicting interannual variability interannual variability in annual area burned, they do a pretty good job. And so if we want to look at climate-only projections, we could take GCM data, apply them to these simple models, and get estimates of what's going to happen to annual area burned throughout the remainder of the 21st century. And this figure is an example of what that might look like. That was from the beginning of my talk. However, we can now not only look at what's going to happen under climate, but also account for what's going to occur when we account for these negative feedback effects. Specifically, if we can develop these models to account for how the negative feedback strength will also increase under climate change, we can potentially get two different scenarios for each ecoregion throughout the remainder of the 21st century. We can get scenarios that give us an estimate of area burned when it's climate only that's driving these changes. And then we can get an estimate of what happens when we actually take into account these feedback effects that we know exist. So how much area burn could potentially be reduced due to these negative fire vegetation feedbacks? This is work I'm still kind of figuring out and doing right now. So unfortunately, I don't have more results to show you today, but we hope to have these results soon and we'll share them when they are available. So with that, I just want to kind of wrap up the key points from today, and then hopefully I can answer any questions you may have or have a discussion about this work. We found that fire-climate relationships are really complex. They're nonlinear and they exhibit these thresholds to burning. And we know that when we look at future climate projections, that these thresholds are likely going to be surpassed in the future, leading to potentially very dramatic increases in fire activity in these ecosystems. However, we also know there's a potential for negative fire vegetation feedbacks to exist and potentially mediate or offset this direct effect of climate on fire. That's what we're working on now. We're going to be able to link these components together and get these explicit projections of annual area burned in the future that account for this feedback effect. With that, I just want to thank you for having me present today. I hope you enjoyed it. And yeah, I'll be happy to answer any questions you may have. Thank you.
Thanks, Adam. That was great. Very cool stuff. I don't see any in the chat. If anybody wants to unmute and ask a question, great. Or if it's easier or your bandwidth limits it, go ahead and push one into the chat and we'll see where we go. None so far.
It looks like
Brendan Rogers and Randy Jant have their hands raised.
This is Randy. I don't know if I had my hand up first or Brendan did. I'll ask my question. So are the variations in FWI across the extent of Alaska and Canada at this point greater than or less than the difference in FWI that you might see by end century? So I'm just trying to figure out, because right now your feedback strength is no place is more than 10%. So I'm just wondering what's the most we could hope for there.
Right. Yeah, that's a good question. I don't have that number off the top of my head regarding variability across what we currently see across all ecoregions versus what we expect in the future. Part of what I'm working on now is actually to get those downscale projections for the future, to get better estimates of that. But right, so right now we have this 10% value. I think we'd have to evaluate and look at, what's a reasonable limit to put on that in the future, because it's just a linear model. So that could, depending on how fire weather indices change, that could, get pretty, become greater than 10% pretty quickly. That's something we're still figuring out. So unfortunately, I don't have a great answer for that today, but that is something that we're aware of, that, when we make these projections, we have to understand that what we're going to look at in the future is likely going to be different than what we've seen in the past in terms of the range of variability. But yeah, that's a really good point. And that is something we're considering and keeping in mind as we do these future projections. I think Brendan.
Yeah, thanks, Adam. That was really cool stuff. I was just trying to understand the relationship you showed, I think, between long-term fire weather index, correct me if I'm wrong, it's not at the time of fire, and the feedback. And it looked like when you have greater FWIs, you have a stronger feedback, right? I'm just trying to understand that mechanism, because I guess in my head, I was thinking, and I've heard from other accounts that, when it's really severe fire weather, the sort of potential negative feedback from vegetation starts to just kind of get washed out because the climate signal is so strong, right? Everything just kind of burns. Whereas when it's, less severe fire weather, that the vegetation might have a stronger effect. And it looks like you're showing the opposite. Am I interpreting that right?
So what this is showing when we're trying to summarize this, we're saying where do we see the strongest negative feedback effect? And we see that it's in ecoregions that have characteristically warmer and drier fire seasons, essentially. So I think your interpretation is correct. The way I'm kind of interpreting these data as it currently stands is that when we have ecoregions that overall will have more extreme fire weather, we might have a stronger negative feedback for several reasons. This could be due to a situation where maybe you have a higher likelihood of repeat fires that would potentially have a higher negative feedback. Fires can be less likely to occur in a landscape if there's been repeat fires, over a shorter amount of time. Fire severity could also change the landscape more, which means that the boreal forest that occurred prior to it under more severe fire is going to be less likely to be there in those 40 years afterwards. Therefore, also having a potentially stronger negative feedback effect. And also, I guess the way I understand it is that when we do have warmer and drier conditions, that could lead to a potential shift to deciduous dominance under some circumstances, which may also explain that feedback. I think there's a lot of different potential drivers that could explain this pattern. I don't know which one it is, and my guess that it's going to vary by ecoregion in exact situation. Does that help kind of maybe clarify what we're looking at here? Or
yeah, definitely. It's just interesting that it doesn't sort of play out on the graph on the right? Like the younger fuel, unless there's like no conversion to deciduous, right? But if it is the younger landscape and you are getting a general trend towards more deciduous, it's interesting you don't see it on the vegetation variable. But maybe it's because you're accounting for the climate one at the same time, right? So
yeah, and I'm also wondering if, because right now we're summarizing these data, both climate and vegetation across the whole ecoregion, and maybe that's too coarse, especially for maybe vegetation composition. We would have to look at, the regions where fire is actually occurring. But, at the scale of the ecoregion, we can at least say that vegetation composition, percent deciduous or percent coniferous or needle-leaf forest is not having any real influence on whether we see a negative feedback or not.
Cool. Yep.
I think Neil.
Yeah. Hello. So I'm not a geographer. I'm a geologist, and I mostly work in the ancient geologic record, but some of that includes boreal environments. And so I'm particularly interested in this idea of temperature thresholds. And you state this. There's an evident increase in statistical chance of a fire at around 13 to 14 degrees Celsius. Is that correlated with anything else that is a factor? Like, for example, of course, you have the evapotranspiration, precipitation minus evapotranspiration, which is implicitly related to those temperatures and their variability. But like, for example, where do thunderstorms kick in? Is there a threshold limit for you don't get big thunderstorms or lightning storms until temperatures above 15 degrees or something like that?
Yeah, that's a great question. Yeah, the idea of like maybe a lightning or ignition limitation in these cooler regions is definitely a potential kind of explanation for what we're seeing here. I know others have looked at that. I have not personally looked at that, so I don't have a good idea of where exactly that threshold would lie with, an increase in lightning ignitions. I do know this threshold, when you look at it, does lie relatively near where you would see kind of that transition in a lot of cases from boreal forest to tundra. But again, kind of like how I highlighted at the beginning, that alone is not going to explain all of it, because there are tundra regions that lie above that threshold and boreal forests that lie below that threshold. And so I do think it has something to do with more conducive conditions to fire weather, and potentially that lightning or ignition limitation goes away. So yeah, that idea is in line with what could be happening here. I don't have a great answer if that's exactly what's happening, but that's definitely a good explanation or potential partial explanation of what's happening.
Yeah, it's really interesting as a geologist and a paleoclimatologist, where we don't know things. These kinds of thresholds that are identified in the modern are very intriguing, because like we go from environments that don't have an abundance of evidence for fire to environments that suddenly there's a great deal of fire, and that notion of a physical threshold that can be felt like temperature is a very intriguing one to people who study deep time. So thanks. I didn't realize that this existed until today.
Yeah, awesome. Thank you.
So Randy's got an interesting observation, Adam, that's in the chat. And she asked if the stronger feedback at the higher FWI has to do with burn severity, so that you get a subsequent effect from the previous event under those conditions.
Yeah, I think that's definitely a potential explanation of what's going on here. I think I mentioned that a little, maybe it wasn't very clear, but yeah, I think it's, this feedback effect at these kind of warmer and drier, in these warmer and drier conditions is something due to either, kind of repeat fire events, or, the fire itself was much more severe and it's going to result in a larger change in the landscape that's not going to be able to recover as quickly. It's going to remove some of that kind of resilience that maybe the boreal forest would normally have. So yeah, I definitely think that's a very good explanation, and a likely explanation in a lot of cases, something similar to that.
And then a related point, not on severity, but intensity. Anthony asked, how are these trends related to predicting fire intensity? So this gets at that issue that we see so often, where we like elements of the full fire regime: area, intensity, frequency, severity, all that stuff. And we often fall into the trap of shuffling back and forth between one and the other without predicting them explicitly. Although Brendan's done some work that gets at that, I guess, more mechanistically. But any thoughts on intensity, fire intensity?
Yeah, that's a good point. I have not thought a lot about kind of fire intensity regarding what's going on here. So no, I don't have an initial idea of whether intensity is playing a large role. I guess I would try to tie intensity in with, if it's a more intense fire, it's going to have more likely to have a larger effect on the landscape, which could be linked to severity then. So yeah, yeah, that's a very kind of reasonable and good guess of what's happening exactly in the landscape when the fire event is occurring. Given the scales we're looking at, I haven't dug into any of that at all, whether it's like intensity or overall severity. my guess is we will end up digging into that a little to help explain this when we're writing this up. But as it currently stands, I don't have a great idea whether, what role intensity is playing relative to maybe other factors.
And then there's a little bit of traffic first from me in response to Neil. It looks like Neil's taken off potentially, but and then also from Randy about the temperature threshold and relationships to fuel drying, fuel aridity, fuel availability, fuel flammability. So the potential indication that somehow around there, at least as a mean metric, you get an increase in the potential for existing fuels to burn.
Yeah, I'm sorry. I'm just reading the message right now to see if I can better.
Well, he implied initially that there was, why 13.4 with, a couple question marks after it. And I pointed out that's the statistical estimate, not necessarily of a population of thresholds that are evident in the data set. But, Randy's talking more about specific mechanisms that would occur there. And we see those in other systems, but maybe less clearly expressed than here, where those are clearly limiting for much of the year, or even in many years, just period.
Yeah, I guess when we're interpreting the results, when we first see the results and we were interpreting them, kept coming back to what is the ultimate driver here, especially since we're considering these longer kind of multi-decadal timescales. And the consistency and just kind of the overall strength of that threshold and how often it appeared suggested to me that this was related doing that, like right around there, around mean climate, at least in these ecosystems, you start to see this nonlinear increase in extreme fire weather conditions for a given year, or a more higher likelihood of extreme fire weather conditions in these climatologically warmer regions, which would lead to such things as overall drier field conditions, which would be much more likely to have a fire and a larger fire. So I definitely think my interpretation has long been that that's been the main kind of driver when we consider these thresholds, is that there is a nonlinear increase or likelihood in extreme fire weather conditions, which would lead to more burning.
All right, any others? All right, thanks, Adam. Thanks all of you. I guess at this point we turn it back over to Meredith.
Sure. Thanks everyone for joining. I also want to acknowledge Mike Folkowski, who's here, who was a team leader for the Terrestrial Ecosystems team and is stepping down to make room for the new team leaders. So thank you for everything you've done for this team, helping direct it. And with that, I think I'll say goodbye. Thank you everyone for joining. The recording will be available on Thursday.
Thank you.